Okay, let's check out this question that is pertaining image size calculations or multimedia. Yeah. So the first question that we have is okay. The paper is from 9618, 2022. That's variant 2, paper 1, of course, May June. So we're being asked that draw a line for each image representing term representation term to its image representation term to its correct definition. So the first one that we have is a pixel, and by definition, when we're talking about a pixel, we're just talking about the smallest unit of a bitmap image. That's how I love it. So it's the smallest unit, right? I usually love to put in the part that they are only found in bitmap images, because an image, basically, an image can be saved in two ways. It can be represented in two forms. It can either be a bitmap image or it can be a vector graphic image, right? That's how an image can come through, vector graphic image. So you see now, when you're talking about bitmap images, its smallest unit is going to be coming through to be a pixel, right? But vector graphic images now, they don't come through in pixels, but they always come out in formulas per se, right? They're going to be presented as a formula per se. The formula on how to draw the image itself. You get the point? They always come through in objects, picture objects. Not drawing objects, I mean to say. Okay? I can have it like this. They always come through in drawing objects. That's how vector graphic images are going to be coming through like. So that's where the differentiation is. So when talking about a pixel now, it's the smallest unit of a bitmap image. That's how I love it to be like. Of a bitmap image. So always know this part. So in this example that we are having pixel, it kind of indicates the smallest identifiable component of an image. This is correct for me. But whenever you are asked to define a pixel, don't leave the part that it has to be a bitmap image. Yeah. So you can always just even write the definition of a pixel, that it is the smallest identifiable component, but of a bitmap image. Make sure that you master that part. So this was supposed to be coming through to be pointing here. So I will go ahead and clear my screen. This is being indicated by this. And the next thing that we have is a bitmap, a bit depth. So bit depth basically refers to the total number of bits. Here, total bits used to represent a pixel. Here, to represent a pixel, or to represent each color, right? That's what is called a bit depth. Check this out. When you're talking about a pixel, let's say bitmap image one more time, we're talking about something like this. So if I have an image like this, it comes through now with the very number of pixels here like this. Right? If I have this shaded like this, right? You can clearly see that this is the letter T that we have right there. Let's just probably edit this one as well. You can clearly see that this is the letter T that is presented by this image. But we are saying how many, okay, what we are calling a pixel is just this one thing. This is what we are calling a pixel. One box, right? The smallest identifiable component of a bitmap image. One box is what we are calling a pixel. Bit depth now is on the part on how many bits we are using to store on this pixel, right? How many bits are used to represent that pixel? How many bits are used to store each pixel? That's the part now of bit depth. So if we're using 8 bits to store each pixel, so be it. That's going to be our bit depth. When we talk about image resolution now, we're talking about the total number of pixels used to represent this image. Here, the total number of pixels used to represent an image. Represent an image. Yeah. So we're talking about the power of what? In this case, we have 1, 2, 3, 4, 5. 5 times 1, 2, 3, 4, 5, 6. So we got 6 high, 5 wide, which makes them 30 pixels. So this will be acting as my image resolution. The total number of pixels wide times the number of pixels high. That's going to be coming through as my image resolution. The total number of pixels used to represent each image. I don't know if that makes sense. Then check this part. Whenever you store an image, whenever you go on the parts like you want to get the file data or image data, right? That's about the image basically. You will see information like the image size, right? You see information like image location. You see information like the image format, either it's a PNG or it's a JPEG, right? If either of these, so all this information is going to be stored on what is called the file header, right? All this information is going to be stored in what is called the file header. So we'll talk about its main definition in a second, but basically, information about an image is stored in a file header. Sometimes they call it metadata. So information describing an image is called metadata, and it's stored in a file header. So the file header always comes with every image containing metadata or descriptive data. Descriptive data about the image itself. That's basically what we have. I hope this is making sense and I hope you're taking notes. So I'll clear this now. So we're saying this is a pixel, bit depth, number of pixels, nopes, stores data, nopes, number of bits, that's what's up. So the number of bits used to represent each color, that's bit depth. Image resolution, the total number of pixels, there we go. File header, it stores data about an image file. So that's what's up. Right? That's how I was supposed to be answering this. So I'll clear my screen again. Then I'll move on to the next part. The following section of a bitmap image is 10 pixels wide, 5 pixels high. In this example, each color is represented by the letter B. By a letter, either B or P for blue, maybe O for orange, P maybe for pink, Y for yellow maybe, R for red, I don't care. So, from this information that I'm giving here, I can already calculate the image resolution, 10, 5. So image resolution is equal to 5 times 10, giving me a 50 pixels. Yeah. Then I'm being told that the colored image, the complete image, is can have 2, 5, 6 colors. So I'm being given a color depth. So I need to know now how many bits do we need for this. So for 250 colors, we can store 250 colors in 8 bits. Right? How can I find this with easy? I can just express any number, the number of colors, right? the number of colors into binary. So this in binary, it's 1, 1, 2, 3, 4, 2, 3, 4. That's 256 in binary. Check this out. If I have a 1, whenever I have a 1 and trailing zeros, okay, the next thing that I'm supposed to do first after I'm changing a number in binary is to count the number of bits that are there. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 256 is being represented in 9 bits. Yeah, but check this part. Whenever my conversion gives me trailing zeros like this, only a single 1 and trailing zeros, I have to less a 1 here, indicating that I'm going to be having 8 bits that are going to be used to store 256. I hope that makes sense. So whenever I have my conversion maybe coming through like this, 1, 0, 0, 0 like this, these are 4 bits, yes, but because we have trailing zeros, we get a less than 1 to get now 3 bits. It's different if I have 1, 1, 0, 0 like this. This way, we cannot call these trailing zeros because we have a 1 here. So this is 4 bits. I hope you meet up a question that is going to be needing you to apply this information. But basically, yeah, that's what's up. When you're given color depth, you can convert it to bit depth by converting the number of colors into binary. So 256 into binary, there's this. But because I have trailing zeros, I have to less than 1 to leave me with 8 bits. That's why I could clearly say that I have 8 bits here. You get it? So we're saying identify the smallest number of bits that can be used to represent each color in the complete bitmap image. So we're talking about what? 8 bits. That's going to be my solution, isn't it? So that's what's up as far as this is concerned. I'll clear this screen and I'll leave this with 8 bits as my solution. Yeah. Then next, we're being asked to calculate, to estimate the file size of the section of the bitmap image, of this section here, right? Giving your answer in bytes. Then use your answer in part P item 1. Okay, we're saying that whenever we are asked to find the image size, image size is always going to be calculated by saying in image resolution multiplied by the bit depth. That's always the case. Image resolution multiplied by the bit depth. So in this sense, I got 50 for bit depth, for image resolution, then I got 8 for bit depth, right? So that's what I'm going to be bringing in here, right? Image size, I will write the point that image size is always equals to IR times PD, so it's now 50 pixels multiplied by 8 bits. I gotta get, is it 400? I have now 400 bits. So 400 bits into bytes now. I gotta divide that by 8 because we're saying 8 bits make up 1 byte. Divide that by 8, this will leave me with 50 again. 50 bytes. That's gonna be my solution. I hope that makes sense. So always remember that image resolution times the bit depth is going to be giving us the image size, but in bits. You want to put it in bytes, you divide by 8. You want to put it maybe in megabytes, you divide by what? 1024. But, oh sorry, that's in kilobytes. That's in kilobytes. You want to put in kilobytes, you divide by 1024. All right? But if you want to put maybe in megabytes, you divide now by further again by 1024, right? But in kilobytes, in KB you divide by 1000, in megabytes you divide by 1000. I hope you know the difference between this and this. This is denary prefix, yes. This is denary prefix, and this is binary prefix. Always know the difference between these two. So that's how we close this up. So I'll clear the screen again to maybe indicate that I just needed 50 here. To indicate that I just needed 50 multiplied by 8 here, divided by 8. leaving me with 8 bytes. Then here, describe how changing the color depth of an image affects the size. So if I change the color depth, right? If I increase the color depth, that means that I will need more bits per pixel, right? I'll need more bits per pixel. And more bits per pixel now, more bits per pixel, means that I'm going to be increasing the file size altogether. You get the point? That's how I would get my 2 marks. I'll first indicate that the color depth is a direct relationship with the what? With the bits per pixel. So if I increase the color depth, I will need more bits to store each pixel, hence increasing the file size. That's basically how you're supposed to be tackling this. Or you would want to go the other way around, that if you reduce the color depth, then you will need fewer bits per pixel. So fewer bits per pixel means that the image size is going to be decreasing altogether. That's how you would solve, you would answer this one. I hope that makes sense. Then the next thing that we have was a compression-related question, whereby we're given the first row containing all these, then explain how this row can be compressed using lossless. Lossless compression, we're saying that we can retain our original information. Original data can be obtained. Yeah? So we are saying that this is going to be coming through. We can use the solution to this. We can use a compression algorithm, right? A compression algorithm. Probably we're talking about run length encoding. It's an example, right? Whereby we are saying we will just count the number of b's of the repeated terms, right? And how many times they were repeated. So I'll be just like 10b like this, or I can say b10 like this. Means that I have b, but it's coming in 10 times. That's how I can compress this. I now have 3 characters, but here I had about 10 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what's up. So I'll be like B10 like this. That's how I would compress it. Because I have just used a compression algorithm, which is run length. Run of B with length. So a run is a sequence of if a sequence of repeated terms. So this is B's run, because B is being repeated. How many times? 10 times. So it's a run and its length type of encoding. That's what we have here. That's how you could have answered this question. I hope that is clear. So I'll clear this, then maybe I'll move on to the second question, which is coming in from May, June 2020, 9608 this time. A digital camera takes a bitmap image, 200 pixels wide, 2000 pixels wide, 2000 pixels, 1000 pixels high. Calculate and estimate the image size. We're saying that it uses a color depth of 24 bits. So you're being told again the number of bits used for each pixel. Then give your answer in megabytes. Megabytes is dictionary prefix. Right? That's 10 to the power of 3. Oh no. 10 to the power of 3, that's kilobyte. 10 to the power of 6 now. That's going to be megabyte. Right? So in this situation now, 10 to the power of 3, these are bytes here. That's 1000 bytes make up kilobyte. 1 million bytes make up a megabyte. So in this situation here, I'll first, they asked me for the file size. So image size, as we discussed in the previous session, is equals to image resolution multiplied by the bit depth. So in this sense, I have 2000 multiplied by 1000 for the image resolution. For bit depth, I need to multiply by 24, right? These are bits. I have to divide this by 8 to get now my answer in bytes. This will cancel with this to leave this with a 3. 3 times 1, that's 3000, times this, that's going to be coming through to be 6. 6 million now. Yeah. Then I'm being asked 6 million bytes. I need to convert this into megabytes, so I'll divide this by a million, or by 10 to the power of 6, which leaves me with 6 megabytes. always remember that megabytes and megabytes, they are different. If they wanted us to calculate in megabytes, it was supposed to come in through like this, right? Whereby I was supposed to be dividing by 2 to the power of, is it 2 to the power of, is it 12? 2 to the power of 10, 2 to the power of 12. You can just cross check how many is 2 to the power of what that we need to be using here, right? That's basically what we have on as far as this is concerned. I'm going to be having 6 megabytes. That's basically what we have. I don't know if there are any questions. Okay, I'll clear this and I'll just be expecting any question if you have one. Then the next thing that we have is an image size is taken. A second image I meant to say is taken. Then the time this time in black and white. So we just used the color depth. The color depth is now 2 colors. 2 colors means I need only 1 pixel. Right? 1 pixel is 1 box. I only need 1 bit, I mean to say, to do that. To store colors, two colors, either a 1 or a 0 here. So a 1 might be for black, a 0 for white. So we are now using 1 bit. But the file size, it is the same number of pixels, of course, but the file size is smaller. Yes, as we discussed before. Explain why. So reducing the color depth means we are now using lesser bits per pixel. Right? Reducing the colors, it means we now need fewer bits per pixel. And fewer bits per pixel now reduces the file size altogether. Reduce the file size altogether. So that's basically what we have there. That's how you would solve this question. Alright, I hope that makes sense. Then the next part now that we are given is the last part after all. A digital camera allows the user to add text to an image. Each text is encoded as ASCII value. Then we are being told that A is for this, B is for this, C is for this, D is for this, and D is for this. They're now saying that give 8-bit binary value. Give the 8-bit binary value for ASCII B. So you're just supposed to be converting this into 8 bits. Pretty simple. I have 1, 2, 4, 8, 16, 32, 64, 128. 1, 2, 3, 4, 5, 6, 7, 8. I gotta convert this now. I gotta convert 98. I definitely need this. 64, plus that's now 96, 96, 97, 98. So this becomes zeros. So that's my answer. That's basically what was needed as far as this part is concerned. So I hope this made sense and you were able to tackle your own questions. Please feel free to touch base with me if you have any question.